Our differential equation we're working with is y prime equals 4 minus y, and we'd like to determine the equilibria and also the stability of those equilibria. So y prime equals 4 minus y, so we have an equilibrium solution at y equals 4, right? So y prime would equal 0, and then we have 4 minus 4 is 0, and yeah, 0 equals 0. This is an equilibrium solution. So the first way we can determine the stability is to plot a direction field. And so right, if we're at 4, we're going to have flat horizontal lines because the derivative is 0. But if we're at, let's say, y equals 5, a little bit above 4, we're going to have negative slope. It's going to be pointing down. And if we go to y equals 6, it's going to be negative 2 slope. It's going to be even steeper, and it's going to be pointing down still. If we're below y equals 4, so like at y equals 3, then we have 4 minus 3. That's positive 1, so we get a positive slope lines. And then if we go to y equals 2, then we're going to have slope 2, so we're going to have steeper slope lines. If we go to y equals 1, we'll have even steeper slope lines. So this is the way they're going. The trajectories are going to go towards this thing. So that would mean, right, they'd look something like this. And so then that would mean that this is going to be stable. All right, so that's the direction field way to do it. Well, what if we were to plot it on this thing? We're doing like y prime equals f of y equals 4 minus y. So we have f of y on the vertical axis, and we have the value of y on the horizontal axis. And if we're at y equals 4, well, it's 4 minus y, so we're going to intercept when y equals 0, we get the value of 4. And then it's a negative slope, so we're doing something like that. Right, and so here, if we look at this, right, this is going to be an equilibrium solution, y equals 4. To the left of the equilibrium solution, we have positive f of y, which means positive y prime, which means if we start over here, the value of y is going to be increasing, so the values are going to move to the right. Right, so we have our arrows, and they're going to get bigger and bigger as we get further and further away. Then on the other side, this is f of y equals y prime. So on this side, y prime is negative, and so if we pick a value, y right here, it's going to have y prime is negative. If y prime is negative, that means y is decreasing. If the value of y is decreasing, that means y is going to be moving to the left on this line. And so we also have different values, right? It's getting more and more negative as we go more and more to the right. So our arrows are going to get, bigger and bigger. It's going to be moving faster and faster. And right, so that also confirms that this is going to be, pardon my poor drawing, it's a stable equilibrium point. Right, another way to tell that is, if, what is partial f, partial y evaluated at y equals 4, the equilibrium point. Right, and that'll tell us the stability as well. So if we take partial f, partial y, well, that's partial y of 4 minus y is f of y, so 4 minus y. Well, if we compute that, the partial derivative of 4 with respect to y is 0, and the partial derivative of y with respect to y is 0. So then we just get 0 minus 1. The slope is negative. And the rule is that if partial f partial y is greater than 0 at equilibrium, the equilibrium point, I'll just say at y equals 4, then that means that it is unstable. And then if partial f partial y is less than 0 at y equals 4, that's going to mean it's stable. And then I forgot my f there, sorry. And if partial f partial y is equal to 0 at y equals 4, then you're inconclusive. You don't know if it's stable or unstable or semi-stable. Inconclusive. And right, so -1 is less than 0, so that actually means that the equilibrium point is stable, and that agrees with the other two methods we used. We used a direction field, we used this kind of phase line plot, and we also used this partial derivative approach, which wasn't too bad because f of y, this right-hand side isn't very complicated.